Okay, so I hope you had a good weekend. So I'm back to continue with the flavor physics at Hadron Colliders. So in our last lecture, we had a we discussed the reasons and motivations for going to Hadron Colliders for flavor physics, and we described what attributes an experiment should have, and we arrived at LHCb, and I will be talking very largely, but not entirely, about LHCb. This is unavoidable. Now, today we plunge into the flavor physics proper, and I want to address CP violation, indeed the wider topic of the unitarity triangle, and how we measure its parameters, and how LHCb contributes to that. So this is my overview. So the last 60% of the lecture will certainly be on CP violation measurements. One thing I think I should emphasize is that this is not an exhaustive list. I've in particular tried to keep the list limited. There's many more CP violation measurements out there, and I encourage you to go and look those up. I'll start with some slides of more general introduction. I hope this will not be given what you know and given what you've heard in the lectures so far, this will be familiar stuff, but I include the slides for reference. Firstly, working towards the unitarity triangle, we know the CKM matrix must be unitary. That imposes various constraints, and these constraints can be represented geometrically as unitarity triangles in the complex plane. Experimentally, the most interesting is this one here, because it gives a triangle of where all of the sides have similar length. But there are other triangles which we will touch on. In particular, there's one very relevant for BS physics, which I give there. So here is that first triangle of the unitarity triangle. Okay, it has a vertex given by rho bar, eta bar, but let us focus on the sides and the angles. Here we have written out fully what those sides and angles are. These angles are familiar, denoted alpha, beta, and gamma, or in Belle II notation, phi 2, phi 1, and phi 3. So the goal of unitarity triangle tests in flavor physics is to over-constrain this triangle by making measurements of all parameters. In particular, it's very interesting to make measurements, measure parameters using observables which are found in pure tree-level processes, because it's difficult to understand how these could differ from the standard model predictions, and those made with loops. In loops, new physics particles may contribute. So we can do two things. We can measure the unitarity triangle as a whole, all of the parameters, just check for overall consistency. But a more refined study is to compare observables and parameters of the triangle measured in tree-level processes with those made in loop-level processes. And of course, we hope to find inconsistencies. This is why we do it. This is this other triangle I spoke of, the BS unitarity triangle. It's drawn in an exaggerated form. This triangle is very squashed. This has an angle which is commonly denoted beta S, or phi s over 2 with a minus sign. And we'll come back to this in the very last topic of today's lecture. Okay, so coming back to the conventional unitarity triangle, here it is in all its glory. You see the triangle as formed by the existing measurements, and I want to walk through these measurements, say a few words about each with a particular focus on how they are measured at Hadron machines. So we're going to start with the two sides. There's only two sides we need to worry about, because the bottom side is 1 by definition. I want to firstly talk about this long side, which you see here. The experimental constraint comes from this yellow and orange circle. This is essentially constrained by mixing measurements. And the tightest constraint comes from a combination of the BD and BS mixing measurements. But as we'll see, it's not just the measurements, but it's also the input from lattice QCD, which turns out to be important here. Some more slides which set out formalism. I think this will be familiar, but I include these for reference, and I'll say a few words. So I hope these will be useful when you look at them afterwards. So we're talking about mixing, so let's say a few words about mixing. I'm sure you've heard a lot about this in the other lectures. So the phenomenon occurs in our neutral-meson systems, for instance, as well as the bees, but also the charm, and I'll be speaking about that tomorrow. And it's physically caused either by these virtual short-range box diagrams or on-shell long-range diagrams. Okay, so the physical states manifest themselves in the B system are, we can call them short and long-lived, so they're very, very similar in lifetime, unlike in the kaon system. These are superpositions of the Flavour eigenstates. So there's these P and Qs, and these P and Qs, they sum up quadratically to 1. So if Cp is conserved, the physical states here are the same as the Cp eigenstates. And this essentially means that the magnitude of Q over P is 1. Now in the kaon system, this is known not to be the case. There's this famous epsilon parameter, which is 10 to the minus 3. And indeed in the other systems, standard model calculations indicate small but finite breakings also. But these have not yet been experimentally observed. The mass and width splittings between the physical states are given by delta M and delta gamma. So if we, so this leads to mixing phenomena, and the values of these delta M's and delta gammas normalized by gamma or 2 gamma respectively, these take a big variation between the systems. So if we focus on the, maybe on the B case, because this is what we're talking about today. So we see that delta M over gamma for the B0 system, that's rather small, but not tiny. Certainly not tiny compared to the charm system, but much less than in the kaon system. Whereas in the BS system, this parameter is large, and this will have consequences in terms of the mixing frequency. And delta gamma, we see, is also rather different in the two systems. It's small in both cases, but significantly larger in the BS system. Okay. So these parameters drive neutral-meson mixing. So now tying it to the experiment, it means that a meson which is initially a B0 has a probability to decay as a B0 bar. Here I'm focusing on the B0 rather than the BS case by way of example, by this expression here. So you see this delta M coming in. So B oscillations are expected. Time integrated B oscillations were seen back in the late 1980s, but time dependent oscillations, where you can actually resolve the oscillations, in the B0 case were first seen at LEP. You see this plot on the left, and now it's measured really, really nicely by LHC. So a real contribution to this measurement. And then in BS's more recently, it was found at CDF, a Hadron collider, and is measured more precisely at LHC. And this plot is so beautiful, I will show it in all its glory on this plot, or on this slide. So here are the BS oscillations, and what you notice, they're very fast. So this is BS going to BS pi, and we compare the case where the BS actually was born as a BS or whether it was born as a BS bar. And how we know that is an important experimental detail which we will discuss. But one sees that the oscillations are very, very fast, but they are beautifully resolved by LHC. This needs very good time resolution. This is where the boost of the B system at the LHC and the very high precision of the vertex detector comes in, and is very important. So I think one of the most glorious plots. Print it out and put it on your bedroom wall. Okay, So let's tie this back to the unitarity triangle. So this oscillation frequency, which is given by the mass splitting, here I show it for the BS case, delta MS, it's driven by this box diagram here, and that box diagram involves the matrix elements, in particular here VTS and VTB. So you see this matrix element coming in squared. But there's some hadronic stuff in front of that. This hadronic stuff we don't need to worry about today, but a lot of it cancels if you form the ratio of delta MS to the equivalent observable in the BD system. But there are effects which are different from both. They're expressed in this parameter here, and this parameter, this psi parameter, must be predictive, must be determined by lattice QCD. So this measurement, so the measurement of the side of the triangle, which is given by VTD over VTS, with a correction coming from the Cabibbo angle, this is essentially coming from the ratio of these oscillation frequencies, but with a correction coming in from lattice QCD. Let me just go back to where we started. So here you see where we are at present. So it is rather well measured. You see this orange line, but the width of that line, I mean, the measurement is now absolutely dominated by LHC B, but to turn that measurement, these respective oscillation frequencies into this band, we also need input from lattice QCD, and that is dominating the uncertainty at present. So currently this is not an experimental problem. Okay, so now to the next side here, which is this left-hand side. This is given by this green arc. Okay, so this is, there's more stuff going on here, but this approximates to the magnitude of VUB over VCB. So this is essentially in the amplitude terms, the difference between the probability of a B to U decay, that's a charmless B decay, compared to the more dominant charming B decay. Okay, so this is what we need to access. Now I'm going to be more brief on this because this is really the province of the B factories, and though I have not had time, unfortunately, to attend all of Karim's lectures, I'm sure he spoke about this. So what we're interested in is the ratio of the B to U and B to C ratios at quark level, but we have to deal with all this hadronic muck because we don't observe quarks isolated, we only observe hadrons. So one needs to worry about what's going on there. So there's broadly two strategies, one inclusive where you look at the momentum spectrum of the lepton. You don't try and actually ask particularly exactly what a meson is decaying, but you just demand that the system is light and therefore consistent with a charmless system. Or there's another case where you actually fully reconstruct an exclusive decay, beta pi, for instance, which would give you the VUB transition. Now, these measurements are dominated by the B factory, so I shouldn't say very much more about them, only to say that they actually are somewhat discrepant at the 2 sigma level. That's not so bad, it used to be worse, but they are normalized by similar measurements made of VCB, and these are even more discrepant. So there are issues here. But I'm supposed to be talking about hadronic machines, so the point I want to make is that though these are measurements where the B factories have led, and I think they probably will continue to lead, there are some very nice complementary measurements coming out of the LHC. For example, at the LHC, we have access to B baryons. That's unique to us. So what we can do is look at the decay lambda B to proton muon neutrino. That's a charmless B decay involving a B baryon, and compare it to the case where it's lambda B to lambda C mu. And so we measure the ratio of these. This is a complicated analysis because it's a semi-leptonic analysis. We don't get all of the particles because there's a neutrino which escapes. but still one can form observables. This is the so-called corrected proton-muon mass, where you see here in blue the actual signal we're looking for, this charmless B decay signal, and this can be fitted and extracted. So we have been able to measure the ratio of these, we've been able to observe this charmless B decay and measure its ratio compared to the charmed B decay, and therefore, again, with the help of lattice QCD, extract VUB over VCB. And because the baryon carries spin, this actually brings extra information to the table. For example, for a long time, this problem in trying to reconcile the inclusive and exclusive measurements here shown in red and purple, respectively, of VUB, these were discrepant, so people tried to explain them in terms of right-handed currents, which are parameterized on this plot by this epsilon r parameter. In the standard model, this epsilon r would be 0. And because the lambda b carries spin, it brings additional information in this plot. And you see it's seeming to favor the actual exclusive measurement. It's lining up with the purple. So this is one example of where the LHC really contributes. And for instance, also one can use BS decays, where you look for the charmless BS decay neutrino decay. But I should really now focus on where the LHC is really strong, and that is actually in the CP violation measurements. So I'll be talking about two angles, beta and gamma. You might say, well, what about, there's another angle there, alpha? Well, I won't be speaking about alpha. Any alpha-related observable involves the same quark transitions as those that are probed in beta and gamma studies. So it's very unlikely to tell us anything more. So I think it is it's a second-class observable, because beta and gamma are things we can measure better. But I shouldn't downplay it too much. Improved measurements are always worthwhile. So any good measurement of alpha is always welcome. But still, let me focus on beta and gamma. Beta first. Again, a few historical notes which are more general than just talking about Hadron machines, and I hope this will complement what you've been told in the other lectures. So beta, most famously, you access this through decays of B zeros into CP eigenstates, J psi K shorts. So this was the first idea of actually trying to make a measurement of CP violation in the B system. And this was first appreciated by famous physicists who are still with us, Sander and Icarus Dighe. Just like to point out this other guy involved, Ashton Carter, who co-signed Dighe's paper of 1981. He left physics a little while afterwards, but he popped up elsewhere. This is actually the same gentleman who was the defense secretary in the Obama administration. So rather unusual cross career, both doing theoretical physics and high-level geopolitics. Right, so J psi K short and decays of B0 into CP eigenstates. So once more, just a few slides to set the scene and to present the formalism, and then we'll cut to the actual experimental niceties. So what matters here is that there's oscillations going on. So you see, what you see is the probability of something that's initially a B0 or a B0 bar being reconstructed in a CP eigenstate, and it depends. You see on the right-hand side, obviously it depends on the decay width, but it also depends on delta M. This is this mixing parameter we've already discussed. But in front of this, you have these parameters S and C, which are given here. I'll talk about those in a second. But what you're really looking at in this process is you have the possibility of a B0 mixing into a B0 bar, or it can decay directly into a CP eigenstate, or it can mix in, then decay into a CP eigenstate. So you have interference between these paths. This expression is written out, I should say, for the case where this width splitting delta gamma is equal to 0, which is an excellent approximation in the B0 system. The BS equivalent expressions are a little more messy. So there are these C and S parameters which appear here. And this is where the CP violation comes in. So there's three possible types of CP violation, as I'm sure you've heard discussed. We can talk about CP violation in the decay or traditionally direct CP violation. This would happen if the actual decay amplitude is different between the process and the CP conjugated process. And this will be very important when we talk about gamma in a moment's time. CP violation in the mixings. This is one category of something that's sometimes called indirect CP violation. This would be the case if these Q and P coefficients had magnitudes where the ratio was different from 1. Now in the B system, this is predicted to be and known to be very small. In the Kaon system, it's observable. And then something which is most relevant for our discussion today is the case where you have CP violation in the interference between these two decay paths. And this is the most relevant, and it's given by the imaginary part of this ratio of QA bar over PA being not equal to 0. So now let us focus on J psi K short. So is this a CP eigenstate? Well, it's got a K short in it. You should know that K short is not a CP eigenstate. That's how CP violation was discovered, but it's very close to 1. And compared to the size of the signal we are expected, we can regard it as a CP eigenstate. So J psi K short is a CP eigenstate. Also in this decay, the direct CP violation, the CP violation in the decay turns out to be very, very small. And one consequence is that this means that, well, that means that lambda CP squared is 1, and therefore this C term, this cosine, the coefficient in front of the cosine vanishes. So these are both assumptions, approximations, but very good ones, and they can be checked and corrected for. And so we're left with having to worry about the imaginary part of J psi K short, because this is giving us this sine term, and this is sine 2 beta, where beta is our angle of the unitarity triangle. So if we form an asymmetry of something which was initially a B0, not B0S, I don't know where that came from, I need to fix that, the J psi K short, B0 bar K to J psi K short to the B0 case, that asymmetry will evolve over time because of the mixing, but it will have an amplitude of sine 2 beta. And what's very nice is that this asymmetry, this observable, is theoretically clean, at least at the current precision. The hadronic effects are very subdominant. So I hope you've already heard that from Kareem. Just to reiterate one point. So what we're really looking at here is this interference, just to emphasize what I said, between the box diagram and the tree diagram, these two decay paths, the mixing and the direct decay. So we're looking, and this interference picks out the vertex I've put here, and this vertex is VTD, and that carries this angle beta. So this is where we get the sine 2 beta from. And what we're assuming when we neglect the direct CP violation and saying there's no cosine term present is that this diagram here, which involves loop level penguin processes, but this is suppressed. It's certainly suppressed, and it doesn't contribute. So at high levels of precision, we need to worry about the effects that brings to the game. Okay, so this proposal, and back at 2001, our Flavour Odyssey began. These CP violating observables were first observed and seen by Barbar and Bell, and from this we got our first measurement of sine 2 beta. The achievement was so significant that we quite rightly got a Nobel Prize, but unfortunately not for the collaborations. But the collaborations discovery, this is a real highlight in modern physics. So you might say, well, this has been measured. Do we need to worry any more about this? Well, we do, because though it's been measured, we want to measure things better. The the measurement which was first performed has shown that to first order, the size of the effect is as expected, but what happens at second order and beyond. So sine 2 beta remains very much a golden observable in flavor physics. Because it involves these box diagrams, this is a place where new physics may well lurk, and therefore we want to measure these with the highest precision. So back after this slightly lengthy introduction to actually LHC B. So LHC B has measured sine 2 beta in just this manner. The measurement I'm showing is with the Run-1 data alone. And the most clean measurement is where we measure the J psi into mu plus mu minus. This is essentially where all of the precision comes from. So here is this. Here is the precision. Now, if you were to hit, so here is the result. A very commendable precision. But if you are to, as I'll show you in a few slides' time, if you are to compare that with the B factories, you'll see it's very similar, but it's not better. This might initially be a puzzle, because the actual sample size we have here, because of the statistical muscle of LHCb, is much larger than B factory. We have something like 114,000 events compared to Barbar's 10,000 events. So why are the uncertainties rather similar? So this is a very important experimental point, which I urge you to understand. The answer comes from flavor tagging. So to form the asymmetry, we need to know whether the decaying meson was born as a B0 or a B0 bar. So to do that, we flavor tag. So typically what we do is we look at the decay products of the other B hadron in the decay, for instance, a muon or an electron from that B, or even a kaon, and that will, the charge of the sign of that muon, electron, or kaon will be related to the flavor of that B when it was produced, when it decayed actually. And so that tells you about the flavor of the other B. So statistically, you know something about the flavor of the B you are interested in. So that's one way to flavor tag, by looking at the opposite B in the event. So sometimes traditionally this is called opposite side. So opposite side, kaon, muon, or electron, that will give you information on the flavor of the B that you are interested in. The B at its production, okay? You may get additional information but by looking at the same side tag. That means that you look at information to do with the B meson you are interested in. For example, you can look at a pion which was formed which comes from the fragmentation process in which our B was produced. And the charge of that pion will have a relation to the flavor of the B that we are interested in, at least statistically. So by looking at these various tags, and there are other tags, we get some information on what was the flavor of our B of interest at birth. Now, you can already see that in many cases, this result may not be right. For example, the B on the other side of the event, though produced as something with a B quark in it, that could actually oscillate if it's a neutral B meson to something with a B bar quark in before decaying. And that would give the wrong flavor tag to the one which we're interested in. So there are dilution effects. So all of this reduces the effective signal statistics. And at Hadron Colliders, this reduction is significant. It's about a factor of 30. Indeed, this is the metric I've written at the top of the slide, which is relevant. There's something called epsilon tag. This is the efficiency of making this tag. So essentially, you take all these possible flavor tags and you combine them together and try and make the best decision, often based on a neural net. And then omega is the probability of mistagging. And if you mistag, that's bad because it's not a neutral thing to do. It means you've actually made completely the opposite decision to the one you want to make. So this enters into our metric with a factor of 2. So epsilon tag times 1 minus 2 omega tag squared. This is the effective tagging efficiency. And this is essentially how much of your real statistics you reconstruct, how much of that is effectively useful for your measurement. And at Hadron Colliders, it's a tough game. If you look at this table on the bottom right, you see what this effective tagging efficiency is. So for the J psi K short measurement, which we looked at, the effective tagging efficiency is just 3%. Now in modes with BSs, it's actually, you can do better because there's other tag modes you can use in the BS system. Also, depending on how the event was triggered, that also tells us, affects how effective the tag is. Finally, as one gets more and more experience, the tagging decision also improves. So one sees a range of tagging efficiencies, and indeed there's even better ones out there, but it's certainly always less than 10%. Okay, so this is as well as you can do at the LHC. Let's contrast this to the epsilon 4s. What's very different here is that the B0 and B0 bar are produced coherently. This means that due to Bose-Einstein statistics, the B's are not able to start mixing until one of these two mesons decays. So this actually immediately gives you a much reduced dilution effect to that which you have at the LHC. And of course, you have many fewer tracks in the event, which also makes life easier. So what one gets is that the effective tagging efficiency at the epsilon 4s is significantly higher than the Hadron machine, about an order of magnitude higher. So this explains why the precisions in the sine 2 beta measurement, and here you can see them, at LHC B, impressive though it is not very different from that at Belle and Barbar, despite the fact that the actual size of the signal sample is higher. But still, statistics win out in the end. This is a run one measurement only, and this will be improved with the full exploitation of run two results, which are coming soon, and indeed further data taking beyond that. But at present, thanks to the ensemble of these measurements, we know this angle beta to be 22.2 plus or minus 0.7 degrees. Now let's turn to the other angle of the triangle, which I consider of interest, and that's gamma. And this has been a particular responsibility of the LHC to improve our knowledge of gamma. When we turned on, the knowledge of gamma was something like 20, the uncertainty was 20 degrees or more. You see this beige pair of triangles here giving you the experimental constraints in 2009. Now that's no good because we want to compare that to the expectation coming from the standard model. So what the predicted value we have now, and this predicted value comes from the other constraints of the triangle, that predicted value has an uncertainty of something like +1 -3 degrees. So we want to get down to that sort of uncertainty before we can make a meaningful test of whether the standard model is describing things well in the flavor sector. So we got to, this is what we're aiming for. 20 degrees does not cut it. So how do we measure gamma? So it can be measured in these tree level decays, which makes things special. So you have two diagrams here, B to K minus D0, B minus the D0 bar K minus. This involves a VCB vertex, it's the dominant amplitude. This is a VUB vertex. This is D0, this is D0 bar. But if you reconstruct these two decays in a state accessible to both, like for instance, K plus, K minus, then interference occurs, and you will pick out interference between the two diagrams, and you will pick out the phase difference between these two diagrams. And that phase difference carries the weak phase gamma. Okay, so there are, as ever, there are QCD nuisance parameters involved, but there are sufficient observables that if you collect together enough decays, you can eliminate those and you can get at gamma cleanly. And what is very nice is that these are tree level processes, which means that they really should not be perturbed by new physics. That might sound counterintuitive. That's not the thing we want. But it is the thing we want here, because we can measure here something which we know very much is gamma in the standard model, and we can compare that with other ways of getting at this gamma parameter from other constraints of the triangle, which may involve loops, and they will be those will be influenced by new physics. And a comparison between the two should show this new physics up. So this approach gives you a standard model benchmark. So we need to reconstruct this D in a way which is common to both D0 and D0 bar. And once you start to work out what the sort of visible branching ratio of the process is, then you're getting down to some quite suppressed decays. For example, this decay, when you look at D going to K pi with this very specific sign configuration, so the D decaying to a different charge K-on to that of the B decay, has a visible branching ratio of something like 10 to the minus 8. But this was not seen at the B factories. We really needed the statistical muscle of the LHC. And it has been seen at the LHC, and you see it here very cleanly. This is from full Run-2 data. Now, what's even more spectacular is we are now separating this decay between B plus and B minus. There's this interference term involving gamma, but this gamma is CP violating. So it flips sign in the B plus and B minus case. And this means that you expect the decay rates to be different in the two cases. And you see it being different. And it is a spectacularly visible and large manifestation of CP violation. People who tell you CP violation is not large in the standard model, if you look at in the right place, it is as big as you can get. And this CP violation is not only large, it can be cleanly related to the phase gamma. That's just one decay with the D going to K pi. There's other decays we can look at, but for instance, even decays where the D goes to a K pi pi 0. LHCb is not very good at pi zeros, but still the sheer statistics we have means that we can still access such modes. In making these measurements, we need to worry about possible pollution as well as the B to D we have a B to D pi mode, and B to D pi is a background process which is an order of magnitude more prevalent. So this would lie on top of the signal. So to reject it, you actually need these rich detectors, which LHCb has, so you can decide whether you're wanting to look for a K-on or a pi-on. So in the top here, we see the reconstruction of a pi-on, the K-on mode. So we've asked the rich to select the K-on, and you get this nice signal in red. And then this blue background underneath the dark blue background is coming from the B to D pi case. And remember, this B to D pi background starts as being 12 times higher than the B to D K signal. Conversely, you can ask the rich to select B to D pi, and this is what you see in the bottom case. Therefore, you get lots of B to D pi, very little B to D K. So experimentally, these are tricks you need to play. As I said, we're now reconstructing B to DK with a D decaying to K pi pi 0. So despite the problem of having the pi 0 here, we are still able to see this decay mode. It's laid beyond the B factories. And again, you see this clear asymmetry. You have a higher signal in B plus and B minus case. And you can look at other decay modes. So these are all of the same sort, B to DK, but we're looking at the D's decaying into different ways. So we can look at the D decaying into a three-body mode. Well, K pi pi 0 we just looked at, it's a three-body mode, but let's look at the K short pi pi case. Here, what we will look at is not just the overall difference in the rates, but we will zoom in the phase space of the D decay. So this phase space is presented here as a Dalitz plot. So we plot the K short pi plus, K short pi minus squared. So this is the decay structure of the D decaying into K short pi pi. You see these beautiful bands here. These are coming from different resonances, such as the K star and the rho and things. But we separate this between B plus and B minus, and we find differences. Okay, you can already see them by eye, and these differences are coming from CP violation. Okay, so these are maybe not as dramatic at first as the clear overall rate asymmetries I've just shown you, but they are very powerful if you exploit them in a quantitative manner. So what we do is actually we take this Dalitz plot and we split it into regions which are chosen by for optimal sensitivity. So we have this binning scheme. You see this in this very gaudy colored plot on the right. Each color corresponds to a different bin. And in each bin, we will compare the rate of B plus and B minus. So where did we get these bins from? Well, these were actually informed by detailed studies of D decay properties made at CLIO-C and BESS 3, where we actually study these D decays in quantum coherent Psi 3770 decays. And this tells us that these bins are optimal, and also it tells us what are the hadronic properties in these bins, the so-called strong phase information. I don't want to go into any more detail, but this is very necessary external information we need for actually interpreting those CP violating signals, which you can see in this plot. We need to get gamma out of this. We need to put in this external information, and this information comes from these other experiments. And it's a very nice demonstration of the synergy between big, powerful hadron colliders and the smaller scale, more elegant E plus E minus charm machines. Okay, so in these regions, we can in these bins, we can compare the rates we get for the B minus and the B plus. So we show these here plotted as asymmetries. And you see that indeed in bins that there is clear evidence of asymmetries happening. And these asymmetries follow a pattern which can be used to extract gamma. And with this, we measure gamma. We measure it to 5 degrees. This is the single most precise determination of gamma. And this is in a mode that people thought was never going to be possible at the LHC. And it's something we have done. And if we combine this mode with all of the others, we measure gamma to a value of something like plus or minus 4 degrees. This will be improved still further when we've thrown in all of the run 2 data. So this is much, much better than the 20 degrees that we started with. But it's still not at the level of the 1 to 2 degrees that the other constraints of the triangle give us. So this is something we will be seeking to improve. And I'll talk about that tomorrow. So just now step back and look at this unitarity triangle. Let's see what progress we've made. This is how it looked in 1995. So, you know, these really big chunky constraints. It wasn't even clear that the triangle really was a triangle. It could have been the constraints are consistent and compatible with a horizontal line. With the turn on of the B factories and the measurement of sine 2 beta, things improve a lot. But still these constraints are very, very chunky. Look how, then we compare this with 2009, essentially at the end of the B factory running, things much, much better. And then from last year with the inputs from LHC B, particularly in terms of gamma, but also the improved understanding of this side here from the BD and BS mixing and lattice QCD, and the contribution to the sine 2 beta measurement. So we are really, we've come a long way. It seems at the moment that the triangle is compatible with the standard model paradigm, but we really should try and test this to destruction. We want to measure these parameters as well as we possibly can. And this is what both Belle II but LHC B over the coming run and the coming decades will seek to do. Okay, finally, yes, I said that it's interesting to compare tree level quantities with which we believe are those coming really as identical to those which the standard model would predict. And there are 2 of them in the conventional unitarity triangle. There's gamma and then this VUB here that is also given by tree level processes. So that gives 1 apex. And we can compare that with the other constraints which come from observables where loop level diagrams play a role, like sine 2 beta, and the mixing, and also results from kaon physics. At the moment, there is reasonable consistency, but there's a need to improve, particularly the precision of these tree level measurements to make this test still more precise. Okay, in the final 10 minutes, and I'll keep it to that. I want to now move away from the unitarity triangle to the one of the other unitarity triangles, which is the one which is relevant for looking at things in the BS system. And I will talk about this observable phi s. Okay, so this phi s is something which it's a CP violating observable, which one can get at in BS decays, and it's very analogous to sine 2 beta. Okay, so it comes about through the interference between a mixing diagram you see here and a decay diagram. So it's a time-dependent measurement which probes the interference between these two. And in the in the BS case, we don't the phase we pick out is not VTD, it's VTS. Okay, so VTS, if you look at the unitarity triangle, is the VTS is shown in the Wolfenstein parameterization. And looking at this top representation of the matrix here, here you see it does not involve an imaginary part. It seems wholly real. So you expect no CP violation. But this representation of the CKM matrix can be written out to higher order. So I've now written below it, I've gone to higher order. I've gone to lambda 4th order, where lambda is sine of the Cabibbo angle. Lambda 4 in the CKM matrix, and now you see that this VTS element starts to acquire an imaginary part. So this means that if you follow through exactly the same formalism as we had for the sine 2 beta case, that there is a phase we expect to be able to measure, and this phase in this case is very small, something like a minus 36 milliradians. And this can be related to the phase of this triangle. In the triangle, in the standard model, this phi s, which is the thing we'll measure, it's just the same as 2 beta s with a minus sign. So beta s, therefore, is something like 18 milliradians. It's a very squashed triangle. Now, this is something which is, again, being driven by a box diagram. So there could be new physics particles in this diagram, contributing both to the BS mixing and to the phase of the BS mixing. So can we observe this? Can we measure it? And can we look for the appearance of new physics effects? And those new physics effects could be easier to see here because the standard model prediction is so small. Okay, so this has been known for some time. And so in the first era of Hadron machines, because it's only Hadron machines where you can hope to see this, the first era was the Tevatron machines. So both CDF and D0 tried to measure this. Now, compared to the sine 2 beta measurement, there's experimental difficulties. We're going to look for something which is analogous to J psi k short. The obvious thing to go for is J psi phi. Now, the problem is J psi phi, it's a vector-vector final state. So this is not so there's contributions depending on the relative orbital angular momentum between the J sine of phi. There'll be different contributions with different orbital angular momenta, and these will have different CPs. So there's a contribution of C plus and CP minus states. So we need to separate these. So we actually need to do an angular analysis of the final state, looking at the kinematics of the J psi and the phi decay to actually work out what are the CP plus and CP minus contributions. Another problem is that the oscillation that the signal we are seeing is on top of an oscillation, and the oscillation is very fast because delta ms is much bigger than delta md. And there's other issues, but let me just stop there. But still, the heroic, the earlier analyses of the Tevatron were very heroic. They were really just pathfinding analyses. They actually had a mild tension with the standard model. They're about 2 sigma away. So this was very interesting and very stimulating when the LHC turned on. You might notice in these plots, the horizontal axis here is this phi s. So D0 measure phi s and CDF plot beta s. So there's a minus a half difference. So the signs are swapped. But also on the vertical axis, you'll notice that this also enters into how the observables are displayed, because there's this delta gamma s, the width splitting between the BS mass eigenstates. So in the BD system, this is negligible, so you did not see this appearing in the sine 2 beta measurement. In the BS measurements, this comes into the game. This delta gamma S is something like 0.1. This is interesting to measure in itself, and it also brings extra handles into the measurement. Okay, so this is something that people knew we could measure at the LHC, and it has been measured. So phi S has been measured now very precisely by LHCb. One has a sample now which is something like 117,000 decays to be compared with 7,000 at CDF. Very, very clean. And here you see in blue on this the actual result which we now have from LHCb, plotted in terms of phi S against this delta gamma S. As well as the J psi phi, there are other measurements which give you sensitivity in this plane. Let me not dwell on what those are, but just be clear that there's other measurements, other ways you can access this angle. But J psi KK, which is how the J psi phi decays, is by far the best way to do it. But it's not, this is a measurement where ATLAS and CMS can also very much contribute, because J psi phi, you can trigger on that using your J psi to mu trigger. And so ATLAS performed a very nice measurement. Here you see their plot of their decay time, and then the angles that they're looking at, and then their final results in the phi S against delta gamma S plane. So this is a result with the full Run-2 analysis, giving the result for phi S and delta gamma S. So here are the numbers, but I will put all these numbers together in a plot shortly, so you don't have to screw your eyes up and focus too much on those. CMS have also done exactly the same measurement again. So here's the CMS measurement. This is on phi S, they have a statistical precision of 44 milliradians to be compared with 36 milliradians from ATLAS, and for LHCb 25 milliradians. So let's see this all put together, and let's see how we have come since the start of the LHC. So this is essentially a couple of years after LHCb turn on. So one has the Tevatron results. These are these big regions here in the phi S against the delta gamma S plane. Here's one of the very early LHCb results, just with a tiny handful of data. This is the combination. We compare this with the standard model. So in the standard model, phi S is expected to be very small, as you see. So projected down onto the horizontal axis, it's very close to zero with a very small uncertainty. Delta gamma S is expected to be something like 0.6, 0.7 with a slightly larger uncertainty. So that's how things appeared, start of the LHC. Now we've had to zoom in on this region. This is where we are now. So huge increase in precision. Let's look at that more carefully. This is a state of the art, apart from the fact that it's state of the art, but that there's still some additional LHCb data to be added for Run-2. So this will improve. But still, it's very interesting to see where we are on this golden observable. And we see that where we are is now shown in this combined gray egg, with all experiments playing a significant role. And we see that now phi S is predicted to be, is measured to be -50 plus or minus 19 milliradians. So this is a very impressive measurement, and it's compatible with the standard model. But what is interesting in my eyes is that it's 2 sigma plus away from zero. So we are now starting to see some evidence of a finite value of this very interesting and important parameter. And maybe the value will turn out to be larger than the standard model. So this is something that we should watch very, very carefully. Okay, so I'm now finishing. The CKM matrix and CP violation lie at the heart of some of the deepest problems in modern physics. The B factory showed us triumphantly that the CKM paradigm is correct at first order, but more precise tests are required. Indeed, many observables are theoretically pristine and should be measured with the highest precision attainable, something we will emphasize tomorrow. Hadron colliders are ideally suited to this challenge, as shown in the measurement of beta, and even more so in terms of gamma and phi s. And the prospects for improving these measurements are outstanding. But there are many, many other CP violation studies out there. I encourage you to go and look them up. Thank you for your attention.
Okay. Thank you very much, Guy. Are there any questions now on the CP violation? No, nothing immediately.
That's okay.
I think.
No questions is good.
Yeah.
It's a long, long day.
It is. It is. So we will see you again tomorrow morning your time, just afternoon for us. But for
yes,
the third
double
lecture.
helping.
Yeah.
Okay.
All right.
I'll see you then.
Thanks a lot, Guy.